All right, welcome back, everybody. Now we're on to section 2.3. This one's all about graphing transformations, transformations of functions, transformations of relations. This is a pretty fun section because you get to take all those graphs and like manipulate them, squish them, stretch them, turn them around, all sorts of cool stuff. Let me pull up the slides and let's get started. All right. So we're going to talk about transforming graphs of functions to begin with. And this is broken down into some categories. So translations, which are vertical and horizontal shifting. So vertical shifting up and down, horizontal shifting left and right. Then we're going to talk about scaling and reflection. We'll split it up into vertical and horizontal again. So vertical scaling is like stretching or compressing. Vertical reflection is like taking something and reflecting it vertically. Horizontal scaling is horizontal stretching or compression, and horizontal reflection is taking something horizontal and reflecting it across like that. Then we're going to talk about multiple transformations because you can do a whole bunch of these things, right? Multiple transformations. Then we'll talk about transforming graphs of relations. Not every graph is a function, right? Not every graph represents a function. And then we'll finish with some Desmos examples. I won't do all the examples, but there's a bunch more on that Desmos like I don't even know what it's called, that Desmos page that you can mess with on your own just to give you some more intuition. So let's get started. Oh yeah, one thing I do need to say outright is you do need to recall the graphs of some of those important functions. You can follow that link again if you need it. But those graphs that we talked about in the previous sections, those ones you need to memorize, you really do want to have those memorized because they're going to show up a lot. Um, yeah, and this is kind of why. So many of the functions that are relevant to mathematicians and scientists are transformations of those basic functions that we saw in the previous section. So you got to know them. What you can do is you can transform, you can combine those functions to make new functions, and producing the graphs of those new functions really just amounts to manipulating the graphs of those other functions that we saw. All right. So for our purposes, the transformations that we are going to discuss are translations, shifts, reflections, and scalings. All right. Here's a little note. So for better or worse, if you remember having to shift, reflect, and stretch different parabolas, maybe in like a high school class, the same theory applies here to arbitrary functions f. So if you remember those skills, you can use them here to save yourself a little bit of time. Right. So let's start with vertical shifts. And I'll go through all this. I'll show you some pictures, and we'll take a look at Desmos as well. So let's say f is a function, and we have a real number c. Let's call this function g of x equal to f of x plus c. So what does the graph of G looks like? It's just the graph of F shifted vertically by C units. So that's what happens here. So basically we're adding some number to the output of F, and that amounts to a vertical shift in the graph. Now, I want to be very, very clear about this. Notice that the addition of C occurs after F is applied, right? So we're adding C to the output of F. So that means that, yeah, so C is applying to the output of the function. And since we plot outputs on the y-axis, that is why we are getting a vertical change. So once again, understanding this function notation is really the critical thing, right? It's the critical knowledge that you need to have. I I remember struggling a lot with transformations when I first learned them, and I just couldn't make sense of them, and I didn't know why. And then when I finally took pre-calculus with Dr. Axler, Dr. Sheldon Axler, he really hammered home this function notation. And once it clicked that this was the output of the function and not just the function itself, everything started to fall in line for me. I was like, oh yeah, that makes sense. That's why we're getting a vertical shift because this is the output and we plot the outputs on the y-axis. So if I start changing the outputs by adding or subtracting stuff, it's going to move things up and down, right? It's going to move the graph up and down. And that's exactly what happens. So here, if the number you add is positive, that's going to shift the graph up. If the number you add is negative, that's going to shift the graph down. If the number you add is zero, No change. There's no shift occurring, right? So here, this is the figure that shows the original graph of f shifted up by 1, and f shifted down by 1. So very intuitive. If you add something to the output of a function, that shifts the graph vertically by however much you added, the value of however much you added, all right? Okay. Now let's talk about horizontal shifts. These are a tiny bit different, but the intuition is the same. So now notice what I'm doing here is I'm going to pick a real number c, and I'm going to shift the input instead. I'm going to subtract c from x. And what this does is this results in a horizontal shift, a horizontal shift. And why is this happening? Because notice the subtraction is occurring before the function f is applied, right? Here's the function f. What we're doing is we are shifting the input before we apply the function. We're doing it to the input, right? We're shifting the input, so we're getting a horizontal change because the inputs are plotted on the horizontal axis, right? Inputs are labeled on the horizontal axis. So whenever you start tweaking the input of the function, you're doing something related to horizontal points, all right? Horizontal points. Now, here's where things can get a tiny bit weird, and I'll do my best to explain it. Please ask more questions about it when we get into the activities. Talk to your friends about it. But if the number c is 0, then this is going to shift the graph of f. I'm sorry, if the number c is greater than 0, this is going to shift the graph of f to the right. Okay? So this is x minus c. If c is positive, this is going to go to the right. If c is negative, this is going to go to the left. And if c is 0, there's no change. So down here, I've got some pictures of, let me zoom in a tiny bit. Here's the graph of f. And now, if I do x minus 3.5, that's going to shift the graph of f this way, 3.5 units. All right, 3.5 units. Here, this is where I'm actually subtracting negative 3.5. So that ends up being a plus 3.5, and that shifts the graph this way, 3.5 units. So what you're seeing here is the shift is the opposite of this sign that you see, opposite of that sign that you see. There's a reason for that. And the main reason, like the basic reason, is that the shift is applied to the input before the function is evaluated. So really what this is like is this is more like pulling the x-axis itself left or right by some number of units rather than the graph itself. So it's a little bit weird, but remember the graph is occurring after you plot it. So here, by changing the inputs, it's like we're taking the x-axis itself and pulling it in one direction or the other. That's like the basic reason for why that's happening. Um, yeah, and so here, if you look at f of x plus c, and you've got a positive c value, remember you can rewrite plus as minus a negative. So that's why the graph is moving in the negative direction. There we go, the negative direction. Um, Here's some more like explanation for that, but I don't know if this is going to make it more complicated or not. So the reason the horizontal shift is opposite the sign is because the relationship g of x equals f of x minus c says the value of g at x, the output of g, is the same as the value of f at x minus c, right? So for example, if c is 5, notice that x minus 5 is less than x, and x is less than x plus 5. So this means that x is to the right of x minus 5, and x is to the left of x plus 5. Okay? So the way that I remember it is it's shifting the axis, not the graph. So everything is reversed, okay? Right. Here's just a general picture. Here's a vertical shift applying after the function is applied. Vertical shift after the function is applied. Horizontal shifts before the function is applied. Before the function is applied. Okay. This is why inputs and outputs are so important. You really have to keep them in order. There's a difference between what's going into the box and what's coming out of the box. Okay. Right. Now let's talk about vertical scaling, and we're going to see this a lot later on too. Um, let's say you've got a function f again, you've got a real number c, If you take the output of f and you multiply it by c, you're going to get a vertical scaling. You're either going to get a vertical stretching or a vertical compression, depending on the size of c. So once again, because the multiplication occurs after the function is applied, this is applying to the output of the function. Yeah, remember f of x is the output. So we're getting a vertical transformation because we're messing with the outputs, right? Here are the details. If the size of C is greater than 1, you're going to get a vertical stretch. And this makes sense if you use that fundamental intuition of multiplication, right? It's basically doing something a certain number of times, or it's stretching something, it's scaling it, right? So if C is like the number 4, well, then you're taking what was the output and you're multiplying it by 4. It's going to be bigger, right? Bigger in size. Now, if the size of C is between 0 and 1, you're going to get a vertical compression because now you're taking less than 1 of that output, right? Less than 1 of those outputs means you're going to go from what was this to something smaller. So when C is between 0 and 1 in size, you get a compression. It's like you're taking half of the value or a third of the value or, 2/3 of the value or anything like that. Um, if C is 0, then you're collapsing everything to nothing. If C if C is 0, then 0 times f of x just gives you 0, and you have the 0 function. If C is 1, no change. C is 1, no change. You might as well not even write C. And those are all the possibilities. Um, Okay, now let's talk about vertical reflection. So if C is equal to -1, so if this thing right here is equal to -1, then all you're going to do is take the graph of f and reflect it vertically about the x-axis, okay? And that makes sense if you remember that f of x is the output of the function, because what you're doing is you're taking the output of the function and you're changing the sign of that output. So if the sign was positive, now it's negative. If the sign was negative, now it's positive. So it's literally taking whatever the graph was and reflecting it vertically. That's what happens. Um, if C has a size that is bigger than 1, then you're not only doing a reflection, you're stretching it or squishing it too. I'm sorry, bigger than 1, you'll stretch it. Yeah, you'll stretch it. So you can combine all these things. Here's a couple examples, a couple pictures. We'll zoom in here. Here's y equals f of x. Now I'm going to scale that function by 3, and that's going to give me a vertical stretch. There we go. You see how it's like the same shape, but stretched? That's what's going on here. Here, I've got a vertical reflection. So I took f of x and I changed the sign of every one of those outputs, f of x. So that literally gives you a reflection, vertical, just like that. Everything reflects across the x-axis. And you can combine these ideas, right? So you could reflect and stretch. So here I actually have the graph of y equals -3 f of x. So not only did I reflect, but I also stretched. Oops, sorry. Also stretched. And that's basically it. Just keep in mind inputs versus outputs. That's the big idea, right? Because we're doing this to the output, we're getting vertical transformations because the outputs are plotted vertically. All right, now zoom back out. Come on. There we go. Okay, now let's talk about horizontal scaling. And what you're going to notice is that the behavior is kind of inverted from what you would think off the bat, right? So now what we're going to do is we're going to take C and we're going to multiply X by C, right? And when you do that, you're going to get a horizontal scaling. Again, the reason that we're getting a horizontal scaling is because we're multiplying before the function is applied. We're applying a transformation to the input of the function before we graph it. That's what's happening. So since the input is affected and inputs are labeled on the horizontal axis, we're getting a horizontal transformation. All right. So anytime you start messing with the inputs, it's going to be horizontal change. All right. Okay. Now here's where things are a little bit backward in some sense, but I'll give you some intuition for it so it's not so weird. If the size of C is bigger than 1, you're actually going to get a horizontal compression. you're going to squish the graph when the size of C is greater than 1. If the size of C is between 0 and 1, you're going to get a horizontal stretching. You're going to be stretching things out horizontally like that. Okay? And then like before, if C is 0, then 0 times anything is 0, so f of 0 is just going to be the initial value of f. If C is 1, no change. So these are kind of like not as interesting as you might think. Yeah, and I've got some pictures over here. I can kind of show you. Uh, Here I've got f of x. Here I've got f of 3x, squished. And then here I got f of 1/3 x. So it's like, it's been stretched out like that. Um, so again, the scaling is applied to the input before the function is evaluated. So you're stretching and compressing the axis instead of the function itself. I like to think of it like this. Do I have this on the next slide? I do. I have it on the next slide. I start it here, but then I explain it a bit more. So the reason that the scaling is like the inverse of the size of C is because if the size of C is large, then the function is running through the inputs faster. It's like if C is a big number, then you're having the function go through it a lot faster, right? It's like the speed in that sense. But if C, the size of C is small, then you're having the function go through the inputs more slowly. You just slowed everything down. So that gives you a big stretch like that. Okay. And I really, really do like to use the analogy of speed. And we're going to see that again in a much more intuitive way when we get to chapter 6, when we talk about trigonometry. So think about C. Oops. Hey, come back. There we go. Think about C as like the speed of the function, all right? So if C is large, the function's going a lot faster and it's going to get through the things really fast, so it's going to squish everything. But if C is really small in size, then you're going to slow everything down and it's going to show up, but much more slowly. It's like a speed relationship, okay? All right. So hopefully that clears it up. Then horizontal reflection. This one is not so weird. If C is equal to -1, then f of -x is just taking the graph of f and reflecting it horizontally. That's all. Just a horizontal reflection. And again, this makes intuitive sense because if you think about what you're doing, you're taking every input and you're changing the sign to be the opposite of what that sign was. So, remember it's like multiplying by -1 on the real line. When you do that, you're taking this thing, multiply by -1, everything switches order. Everything's like opposite. And again, we're doing this to the inputs. That's why we're getting a horizontal transformation. So here's an example of some of those. But I shifted things vertically a bit for clarity. Here's the graph of f of x. Here's the graph of f of -x. So it's literally taking this and reflecting it across the y-axis. There you go. You could also reflect and squish or stretch. So here what I did was I compressed the graph of f by a factor of 3. That's why it's going a lot faster. And then here I'm reflecting it. So here I compressed it by a factor of 3, but then I also horizontally reflected it. So this is getting reflected like so. There you go. So you can combine these transformations, which we're going to talk about in a sec. Here's sorry, let me zoom out. Here we go. Here's a picture of just multiple reflections, or sorry, multiple transformations just on the same graph. Here's the original graph of f. Here's 1/2 f squished because we squished the outputs by a factor of a half. Here's a reflection of f. We took f and we reflected it. So same graph, but flipped over the x-axis. Here's f, but stretched vertically. I stretched it vertically. Here is the graph of f of -x. I reflected it horizontally. And then this one, I reflected horizontally and squished it. There you go. That's the idea. Um, Now, let's talk about multiple transformations. So, in reality, we're probably going to end up doing lots and lots of these transformations, like combining them in a lot of different ways. So, we often want to perform multiple transformations, or there may be a graph that we can interpret as a more basic graph with multiple transformations applied to it. So, very much think about those important graphs that you're supposed to memorize and tweaking them in all sorts of ways, squishing, stretching, reflecting, shifting, up, down, left, right. That's what we're talking about doing, okay? Um, yeah, my tip to you, keep in mind what is going into the function and what is coming out of the function, right? So the order of the transformation matters. Is it applying to the input? Is it applying to the output? Keep that function notation in mind. So I know I sound like a broken record now, but remember the symbol f of x. The stuff inside the parentheses, that's the input. Whatever is going in between these parentheses, that's the input of the function. And this is the output of the function. Okay? That's going to be really important right now. Okay. So here's one that I want you to think about. Remember what I just said a second ago, all right? So my question to you is consider this function right here, f of 2x minus 3. My question to you is what is the input of f? Right. Okay, now say something out loud. What do you think the input is? You can say it to your dog, to your cat, to your computer, to your friend if you're watching it with them. What's the input? All right. Okay, now we got to be careful because remember the input of the function is the stuff in parentheses. Okay, the input of the function is the stuff in parentheses. So in this case, the input of the function is 2x minus 3. It is not x. It is not x. The input is the stuff that goes inside the box. And in this case, let me do this. In this case, 2x minus 3 is what's going inside the box, not x. We're taking 2x minus 3 and dropping it into the function, right? The function. So notice that what's happened is the value x has already been transformed before we apply the function f here, right? So there's a subtle point. That's the input. That's the input. X is not the input in this case. 2x minus 3 is the input. So what you can think about it is this, or what you can think about it like is this. You can think of this as the function f of t, but t is equal to 2x minus 3. T is equal to 2x minus 3. So we've altered the input of the function. I'm sorry, we've altered x before we put it into the function. Okay, next question. How would you transform the graph of y equals f of x to get the graph of y equals 2x minus 3? So think about this one for a minute. Okay, now say something out loud. Yeah, say something out loud to yourself. Give your brain that feedback. Say it to your dog, your cat, your hamster, whoever. Right. Okay, now let's talk about this one together. How are we transforming the graph of y equals f of x to get the graph y equals f of 2x minus 3? We've got to be a little bit careful here because the input of this function is x, but the input of this function is 2x minus 3. So we got to be a little bit careful. Yeah, so with this expression, 2x minus 3, 3 is being subtracted from 2x, not from x, right? It's being subtracted from 2x. So 2x is being shifted by 3 units, not x. You might have said there's a shift, right? There's a shift going on because we're subtracting from something. So there's a horizontal shift. But the catch here is we're not subtracting 3 from x. We're subtracting 3 from 2x. But when we plot the graph of a function, y equals f of x, we're plotting x's versus y's. We're not plotting two x's versus y's, right? Think about the label on the axes, right? This says x and this says y. This doesn't say 2x, right? So what we need to do is we need to isolate that x. We need to isolate the variable x so we can really see what's going on with the transformation. And that's what I do right down here. So What I'm going to do is isolate the variable x. I'm going to factor out 2 from 2x and from 3. So I'm factoring out a 2 from here and a 2 from here, and I get this, 2 times x minus 3 halves. 2 times x minus 3 halves. Now, this is great because x is now isolated, all right? X is isolated. So what's happening here is the graph of y equals f of x is being shifted 3 halves units to the right and then compressed by a factor of 2. That's what's happening. So the shift is actually 3 halves. It's not 3, it's 3 halves because x is being shifted by 3 halves. That's the idea. So the general idea is once you've isolated the horizontal axis variable, in this case x, then you just work from inside to out. So x gets shifted by 3 halves, then it gets compressed by a factor of 2, then the function is applied. All right? Okay, we're going to see this a lot in the activity. You're going to get some really good practice on the homework. The homework for this section is really good. There's a few graphs where you're going to do these multiple transformations, and you're going to get to plot all these points and see where they go, okay? Um, but now what I want to talk about is transforming graphs of relations. So the transformations we've been talking about, scalings, reflections, they can apply to more general relations and just more general graphs. Doesn't have to just apply to functions, all right? All you really need to do is keep in mind which variables are being affected by which operations. So we're going to start with a circle because a circle is a good example of something that's not a function, but it is an easy graph to visualize, and the transformations of the graph are also easy to visualize. So here is the standard form of a circle with radius r centered at the origin. We just saw this in the last section. This is one of those graphs that you need to have memorized, the graph of a circle centered at the origin with radius r, okay? Yeah, like I said, this is not a function of x, nor is it a function of y, but we can still transform this graph by manipulating these variables in different ways. So here's an easy example. Um, let's consider the circle of radius 4 centered at the origin. And what we want to do, oh, sorry, centered at the point 3, -2. So that's this red circle that you see right here. How do we get that circle from the circle that is centered at the origin? That's the question. All right. So just ponder that for a second. Ponder that for a second. Okay. And then maybe say something out loud. How would you get this circle from the circle centered at the origin? Right. So we're not changing the radius. All we are doing is changing the center. So what we can do is we can basically take the circle centered at the origin of radius 4, and we can shift the center 3 units to the right, -2 units down, or just 2 units downward, I should say. So we're literally taking this point and we're moving it to here, maybe more specifically, we're moving it along the vector 3, -2. This is why we were talking about that in section 1.5 when, again, algebra and geometry are, best friends. Uh, so what are we doing? We're doing this. So we took the x values and we shifted them to the right by 3. And then we're taking the y values and we're shifting them down by 2, down by 2. Radius is unchanged in this case. And that's what we've got right here. So you take, literally, you take this blue circle, not too bad, and you move it along the vector 3, -2. Starts here, gets shifted here, and this is what it looks like. Oops. Right, let me highlight it right here. There you go. Not too bad. Okay, now let's do another transformation. Okay, so let's consider the circle of radius 3 centered at the origin. It's got this structure, right? X squared plus y squared equals 3 squared. That's the standard form of a circle centered at the origin. Check out what happens here. If we replace y with 2y and we replace x by 3x, then what's happening is we're going to get a vertical compression by a factor of 2. Literally, like replace this variable y with 2y. What does this do? It gives you a vertical scaling, right? And because this number is bigger than 1 in size, you're going to get a stretch. You're getting a stretch, right? Oh no, what am I saying? A compression. Faster, right? Faster. See, it'll even throw me off sometimes. It's going a lot faster, so it's going to give you a squish, right? A compression. And here, if we replace x by 3x, you're getting a horizontal compression. So what does this do to the circle? Maybe you could imagine it takes your circle and squishes it by those factors in those directions. So we're squishing it this way by a factor of 2, and we're squishing it this way by a factor of 3. Okay, so literally this point here is going to move to this point right here. So 3 goes to 3 halves, right? Multiply it by a half. Negative 3 goes to negative, oops, typo, negative 3 halves. That should be negative 1.5. And then here, this point, negative 3, we're squishing it by a factor of 3. So it's going to go to negative 1. This one's going to go to 1. And this is how we create an ellipse. So how do you create an ellipse? Well, realistically, an ellipse is just a deformed circle. So you take a circle, you stretch it in the horizontal direction, you stretch it in the vertical direction, or compress it, you scale it in the horizontal and vertical directions, and you get an ellipse. That's how ellipses are constructed. So this is how we performed that transformation, changing the x, changing the y. But it's not quite in what we call the standard form of an ellipse. So we can get it into standard form by manipulating things a little bit, and I'm going to talk about that right now. So first thing we're going to do is divide both sides by 3 squared. Right? 3 squared divided by 3 squared is 1. Uh, this 3 squared divided by 3 squared is going to give you 1 also. And here we're left with this. Now, I'm doing a little bit of messing around here. I'm going to explain this in just one more slide. But this is now in the standard form of an ellipse. Don't worry, I know there's fractions over fractions. That's okay. It's okay to have fractions and fractions. Remember, this is just a number. If you want to write it as 1.5, you could write it as 1.5. Don't worry. So this is the standard form of an ellipse centered at the origin with vertices plus or minus a comma 0 and 0 plus or minus b. Okay, just like this. So what we're doing is we're taking x, we're dividing it by a. We're taking y, we're dividing it by b, squaring those things, and then adding the results. And this side is always going to be equal to 1. This is the standard form of an ellipse. Okay, that's the idea. Now let's kind of talk about this structure a little bit. So this form that I've got up here, you could rewrite it like this. This goes back to what we talked about back in section 1.1. X over A is 1 over A times X. Y over B is 1 over B times Y. Okay. So in particular, what's happening is the multiplication by these two factors occurs before the squaring. So the behavior of the horizontal and vertical scaling is inverted, just like we had talked about before, right? So if the size of A is bigger than 1, then we're going to have a stretching in the horizontal direction. In this case, if this A is bigger than 1. And if the size of A is between 0 and 1, you're going to have a vertical compression in the horizontal direction. And the same is true for B. Let me think. I always got to pause and think about these. Am I mixing myself up? Do, do, do. Stretching in the horizontal direction. Yes, that's right. Yes, 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 yes. That's right. Because A is down here, so we're getting a stretch. Whew, throwing myself off. It's always good to ponder and pause and think about these things. Okay, so go back to that example we did, or a related example here. Consider the ellipse 5x squared plus 3y squared equals 1. So what's happening is there's a horizontal and a vertical compression going on, right? Because this number is, we're going through the horizontal values faster and we're going through the vertical values faster, right? Just like that. But this is not in the standard form of an ellipse. So to get it into standard form, this form, right? To get it into that standard form, we're going to use a technique that you're going to use a lot in Calc 1. And that's why I wanted to introduce it this way. And that's why I gave that particular example. So to get it into standard form, we're going to use this handy trick. Remember this for Calc 1. We're going to be sneaky and we're going to rewrite m as 1 over 1 over m. Let me zoom in a little bit. Yes, this is an equality. These two things are equal, all right? So m is equal to 1 over 1 over m. Maybe you can think of it as remember you flip and multiply when you divide like that? That's essentially what's going on. 1 second. Okay, there we go. Zoom back out. Come on. There we go. So in this example, we can rewrite 5 as 1 over 1/5. And 3 is 1 over 1/3. And this is how we can write it in standard form. This becomes this, and this becomes this. And A is equal to 1/5, and B is equal to 1/3. So now it's in standard form. All right. Okay, now to kind of finish things off, let's take a look at some Desmos examples. I feel like this stuff is a lot easier to see when you can manipulate a graph at will, like live on the spot. It's one thing to look at standalone like pictures, it's another thing to physically see it. So you can follow along on Desmos if you would like. You can do this after the lecture, anytime you want, but let's take a look at this function or a couple functions and a circle and deform it a little bit using these transformations. Where is it? Right here. Okay. We'll get to the circle in a minute. Hey, let's look at this function. So this is the good old sine function. We talked about it a little bit in the previous section. We're going to talk about it a lot in chapter 6. We're going to talk about it a little bit right now. So what I'm doing here is I've got a sine curve, the graph of a sine curve, and I've got, excuse me, all of these variables that I'm going to use to manipulate it. First one I'm going to manipulate is D. Notice that this is being added after the function is applied. So we're going to get a vertical transformation. And remember, this type of vertical transformation gives you a shift, right? If D is positive, it shifts up. If D is negative, it shifts down, just like so. Okay, let me set D back to 0. Now let's look at A, okay? So A is taking the sine function and stretching it or compressing it, depending on the size of A, right? So here A is 1, but if I increase A, it stretches the graph vertically, right? Now let's go back to A equals 1. No change. Now look what happens when I shrink the size of A. If A goes between 0 and 1. If A is like 0.9, 0.5, we're getting a vertical compression. We're taking all those outputs and squishing them by a factor of 1/2. Now let's reverse things. So let's make A negative, and what you'll notice is we get a reflection. Zoop. There it is. Zoop, zoop. Positive, negative, positive, negative. So it's literally reflecting the graph through the x-axis. And this is all vertical stuff because we're doing this after the function has already been applied. All right, let me put this back to 1. Okay, now the next thing I want to do is I'm going to change C. And by changing C, I'm going to get what? What do you think? That's right. We're going to get a horizontal translation. So if C is positive, everything's going to go to the right. If C is negative, it's going to go to the left. So by changing C, we're getting horizontal translations, horizontal shifts. Okay, let me put C back to 0 for now. And then the reason that I like to use this graph is because the next variable we're going to tweak is B. And now B is multiplying X, right? So what we're going to get is we're going to get a horizontal scaling. So if B is larger, what happens? If the size of B is greater than 1, what does that do horizontally? Squishes it. Here we go. Check it out. There you go. Maybe I should go. That's better. Yeah, again, because now we're running through the inputs a lot faster. We're running through them faster than we were before. So the graph is going to get squished. It's going to happen faster. Now, let's take B, set it back to 1. There's our standard graph. Now look what happens if I lower B. If the size of B is between 0 and 1, I get a stretch. Now it's going much slower, getting stretch. Vertically, there's been no change. It might seem like there is, but there's no change. This is still 1. Down here is still -1. So as B changes, that's not changing the height at all, right? Now, if B is negative, we get a horizontal reflection. Here we go. Zoop. There it is. Zoop. Horizontal reflection. There you go. And then you can combine all of these things. You could do all of these different kinds of things. Vertical stretch, horizontal stretch, or compression. I should say scaling. Vertical scaling, horizontal scaling, horizontal translation, vertical translation. Like you can mix all these things together. All right. Okay, how about, okay, let's set B back to 1. C is 0, D is 0. Okay, let's take a look at this good old quadratic. So now we're squaring. This is the squaring function, right? Again, if I change D, I'm getting vertical shifts. If I change C, I'm getting horizontal shifts. If I change A, I'm getting vertical scalings, stretching it vertically. If I change B, I'm getting horizontal scalings, just like so. If B is negative, it reflects, just like that. So you can mess around with this on your own if you would like. Next one I wanted to look at is the circle. Here we go. So this is the good old circle of radius 1, the unit circle. Sorry about that. If I change the radius, whoa, sorry. Should keep the radius positive though. Let's make radius between 0 and 10. We'll make the step 0.1. All right, here we go. There we go. Changing the radius. Now I want to set this back to 1 for a sec. And then notice what I've got here. This this is going to apply a shift in the horizontal direction. X minus h gives you a horizontal shift, right? If h is positive, it goes to the right. If h is negative, it goes to the left. That's a horizontal shift. Y minus k, that's going to give you a vertical shift. K is positive, it goes up. K is negative, it goes down, just like that. Because this is happening before the squaring, right? So the signs are doing what they should, just like that. And now here's the fun part. If I change A and I change B, there it is. It's getting squished. So if it's written in this form and A is large, you're squishing it horizontally. And let's look at B. There we go. Or I can stretch it out like that. Stretch it out really far. If B is very tiny, there we go. Stretching, just like that. Cool stuff. So again, you can mess around with this on your own. There's a lot of different examples in here. We can talk more about it in class, and we will definitely do it during the activity. Okay. So on that note, I think that's it. I think that's it. That's right. Let's play. All right. So that's it for transformations. I will see you all in class, or your instructor will see you in class. Thank you again for watching and listening, and I will see you next time.